All right, good morning everyone, and once again welcome back to Algorithms and Data Structures. I just realized I forgot to set up my webcam, so bear with me a second while I get that set up. In the meantime, you can let me know whether you can hear me. The seeing we'll get to in a moment. Let me just mute myself here before making more noise to install my phone. All right, there we go. And this should also work. Yes. All right, good morning. And once again, welcome back to ADS, our last real structured session, although structure is already a relative thing here. Before we begin today with some exercises I prepared, I have an old exam question for you from the analysis exam. I have an implementation exercise that, well, is similar to an old exam exercise. And one more implementation based on your questions from yesterday. But before we begin, are there any more questions about the exam or the course in general? So Todd was asking, is there a list of paragraphs from the book just before the lecture started? I said, no, not really, but I can compile one. Good to hear someone's actually reading the book. Last year, everybody complained that reading the book was not necessary. But good to hear someone is, so I can get you that list. It's gonna be a lot, but I can definitely get you the list. I have the book here in front of me. But are there other questions about the course or the exam? Is there a minimum grade for the exam? No, only for the weighted average of the midterm and the end term. So Siroy, you only need to have a 5.75 as the weighted average of your midterm grades and the take-home exam. Naomi, could I make an overview of what you are allowed to use during the exam? Specifically, can you use the slides? Yeah, so we touched upon this a little bit yesterday too. I can include it in my overview of what book sections, but essentially the book, WebLab, and Brightspace. So anything you can find on one of those places. Does that help, Naomi? I'll include it in the book list thing later, but WebLab, Brightspace, and the book is the short answer. Okay, are there other questions that you have already? Are you allowed to use a summary made by yourself? No, you are allowed to use WebLab, Brightspace in the book, and nothing else. It's open book, but not bring whatever you like. For the record, originally, of course, the course was planned to not have an open book exam. My exam should still be doable without any of these materials. It's not that since you have the materials, you have to use them, right? You can use them. Personally, yeah, okay, but of course, as a teacher, this might be different. But personally, I find if I have to look things up in the book still, that usually takes me quite a lot of time. So the question is whether you will have that time or not during the exam. But that will differ a bit for everyone. Right? So all I'm trying to say basically is don't rely on it too much. Right? There are some basics you should still know. But this is of course true for any open book exam. Is there anything else, or shall we get started here? Give you a couple more seconds to see if any questions pop up. Otherwise, we're going to start. All right. So, yesterday, we talked about P versus NP, problems that are easy to solve versus problems that are easy to verify. Well, for our first exercise today, I've set something up in WebLab. We'll take a look at the vertex cover problem. Vertex cover, well, you can read the description of for yourself in a moment. What I want to do is show that that problem is in NP, meaning that given a solution in our code here, sol, we can verify this solution in polynomial time. So the only objective here is to write a bit of code that verifies a solution to vertex cover in polynomial time. I'm going to give you about 10 minutes to work on that. Just like last time, let me know in chat if you're done early. And if you have any questions, of course, feel free to ask them as well. So first exercise of today, proving something to be in NP in WebLab. We are going to show that vertex cover is a problem in NP by showing we can verify a solution in polynomial time. I'll give you about 10 minutes. Okay, so some people let me know that they are done with the exercise. So let's try, and also the 10 minutes have passed. So let's see if we can figure this out together. If you were done, well done. If you were not done yet, but still working hard, well done too. If you haven't even started, well, there's room for improvement there. So, vertex cover. Given a graph and an integer k, is there a subset such that the size of the subset, so a subset of nodes, at most k nodes, so that every edge has at least one endpoint in this cover? Yeah, so we're basically looking to pick some vertices so that all of our edges are covered. Okay, well, we don't need to solve the problem. All we need to do is, given a solution, this solution sol, verify the solution. Well, what criteria does the new solution need to have? Well, the size of it needs to be at most k, and every edge needs to have an endpoint in this set. So let's start simple. If the size of the solution is larger than k, well, then this thing is not a solution. Otherwise, what do we need to check? Well, we need to check for every edge in the graph. Let's see, graph, all edges it's called, okay. It gives us a list of edges. What is an edge? An edge is a thing with an A, a B, and a weight. All edges. An edge is a thing with an A and a B and a weight. Okay, so if A is not in our solution and B is also not in our solution, well, again, that means we have found a reason to reject this solution, because we have found a reason, or we have found an edge that is not covered by this set of vertices, meaning this is not a complete vertex cover. And if those of these checks never trigger, then great, we have found a solution. So this should be all, and it is. Right, there's only two criteria to check here. First of all, is the length of the solution, so is the size of the solution okay, and then is the content of the solution okay? Does it indeed do what it needs to do? Now, technically speaking, if we want to be real nasty, but as you can see, our spec tests don't check for this, there could be one more thing worth checking. What could that be? Any idea? Exactly, Gert. Whether sol is actually a subset of V, right? Meaning whether everything that is in sol is also in the graph. So we could also still check for S in sol if, let me see, all nodes gets us a list of nodes. Okay, and nodes have IDs. Then let me first do this. Oh, there goes my phone. Let me try and make it a little bit sturdier. Okay. So indeed, Sophia, as you also say, right, we need to check whether all nodes in the solution are actually in the graph. So node IDs in graph would be this, right? All of the node IDs for the nodes in the graph. And if S is not in node IDs in graph, we should return false. But like I said, we didn't have any spec tests that check for this, so it doesn't add anything here. But technically speaking, it is a requirement and we should check for it. In fact, I should make a note that for next year, we add a test for that. Doesn't all nodes already return the IDs? Asks Xijing Chen. I don't think so. All nodes returns a list of nodes, so no. We could just use g.nodes. Sure. So g.nodes has a dictionary of int to node. So g.nodes and then the keys of that are indeed the integers, are indeed the IDs. Yeah, we could use that. But if we want to go there through a function, we need something like this. So alternatively, we could do this in Python. I always forget. Let's see. Yes. Should be dot keys. Yes, in all nodes we have return self.node.values. You are most right, Xijing. But the values of this dictionary, right? So nodes is a dictionary, and values gives us these. So that gives us node objects. Right, so a dictionary has keys and values. The keys are the IDs here, and the values are the nodes here. Does that make sense? Good. All right. Are there other questions about this exercise? If not, then I suggest we move on to the next thing. So the next thing is one from the analysis exam of last year, or the example end term, I don't know, one of the two. Here we have two variations of a problem. We have an unweighted graph G, and I ask two questions about it. Namely, is there a cycle of at most length k and of at least length k? Now it's an unweighted graph, so the length of a cycle is simply the number of edges in it, or the number of vertices, whichever works, right? There's a difference of one, doesn't matter. So given an unweighted graph, is there a cycle of at most length k, that's the short cycle problem, and of at least length k, that's the long cycle problem. Now both of these problems are in NP. I'd like you first of all to show that. And then one of these is also in P, meaning we can efficiently solve it instead of just check it. And I would like you to tell me how we can do that as well. So for the person who asked yesterday in the feedback fruits thing, what kind of questions can you expect about P versus NP? This is an example, right? I give you some problems. I want you to show that they are in NP, either in implementation, as we just did with Vertex cover, or just on paper, as we're doing now. And there could be small variations of the problem that are in P, and it's up to you to identify them and tell me how you could solve them. Okay, I'm going to give you another 7 minutes or so to work on this. As per usual, let me know in chat when you think you're done. And if you have questions, please ask them in chat as well. Okay, so let's start with the easy, whatever easy may mean in this context, the easy part. Naomi and Yola, both well done on getting it done in time. So let's show that these problems are both in NP. How do we go about doing that? What do we need to do? How can we prove such a thing? Yeah, both problems can easily be checked by taking the solution and verifying it's a cycle by checking if every successive node is a neighbor to the previous one. And with the length of the solution, we can check if the cycle is indeed less or more than k, or equal to k. Exactly, right? So these are the two things we have to check. In order to check a solution, we are given a solution, meaning in this case, we are given a list or an ordering or whatever, a collection of nodes in some order. And what do we check? Well, we check, are there indeed k of them? And then we check for every successive pair, is there indeed an edge from one to the next? Yes, exactly. Now, let's... there was one more thing here I wanted to say. Yeah, so just like with the previous thing we saw, right, with vertex cover, perhaps we should also check, okay, the vertices that you give me, is there an edge between them? Yeah, I guess that already implies that they are in the graph. Okay, never mind. I thought of saying we should also check again that they're part of the graph, but well, we check that implicitly by checking whether there is an edge between them. So indeed, given this collection of vertices, we check, is there the right amount? So is it less than k or more than k or equal to k, whatever we need based on our problem. And is there an edge between every pair? Good. So that's verifying a solution, in other words, showing the problem is in NP. Now the question is, of course, which of these is in P and how can we show that? Let's see if anyone has any ideas on that. Okamon, if you have a cycle ABCD, you also need to check if there's an edge between A and D, right? Yeah, you're absolutely right. So we should also check in, well, one of two things. Either the last and the first vertex should be the same, right? That could be a way to encode our cycle. Or indeed, we should check if they're not the same in the collection we get, then we should check whether we can go back. Yeah, sure. So it depends a little bit on how the cycle is encoded. I believe, if I'm not mistaken, that I previously defined the cycle to start and end with the same vertex. So if we get a cycle as a solution here, the first and last vertex would have to be the same. Good. So which one is in P? Which one is the easy problem? And which one is, well, maybe in P, but we don't know. Long cycle. Find the shortest path from V to itself using Dijkstra with extra constraint that the path needs to be larger than 0 for every vertex. This will take blah time, which is polynomial time. Then take the shortest. You found the shortest cycle. Ah, so you start your answer with long cycle, Naomi, but I think you mean short cycle? If you could just confirm that for me. Ah, maybe yes, maybe no. Okay. So you give a nice idea, right? From every vertex, we're going to do some sort of exploration. You mentioned using Dijkstra. Sure, why not? I'll mention something else in a moment. But from every circle or from every vertex, you do some sort of exploration, looking for a cycle, a way to get back to this vertex. Now let me start by making a stupid observation. If the graph is undirected, right? Our problem doesn't mention whether the graph is directed or not. But if our graph is undirected, then I can trivially make a cycle of length 2. Take one edge, and I can take the edge one way and take it back. I've created a cycle of 2 nodes. So is there a cycle of at most length k? Well, if k is at least 2 and there's at least one edge, then in an undirected graph, the problem is trivial. In a directed graph, the problem is indeed still very easily solved. You could use Dijkstra. I would argue Dijkstra is already a bit of overkill. It's an unweighted graph, so we could just use a BFS or a DFS that goes to at most k steps. So at most k distance away. Right, so let's use BFS because that's easier to keep track of how far away we are from our starting node. So with BFS, we can simply check all nodes up to length k away. And if we ourselves are also k away from ourselves, meaning there is a path of at most length k that gets us back to ourselves, then we have a cycle of at most length k. So short cycle is the easy problem here. We can just do a k-step BFS from all of the nodes. That can be done in polynomial time. Long cycle is actually an NP-complete problem because take k equals v minus 1 and you have exactly the Hamiltonian circuit problem. A problem you're not familiar with, but it is an NP-complete problem. If k is 5 and you find a cycle of length 3, you know the answer is yes. If you found one of length 7, you know the answer is no, of the long cycle problem, right? No, but the longest cycle problem asks, is there a cycle of at least length k? So in your example, right, with k equals 5, if you find one of length 3, that doesn't tell us anything. We don't know if there is one of length 5 or not. We do know that there is one of at most length 5, namely the one with length 3 that you just found. So your methodology is exactly correct, but for the short cycle problem instead of the long cycle one. Right, with the use cases you're describing here, we can indeed answer yes and no for the short cycle problem, namely is there a cycle of at most length k. I hope you don't hear the Skype notifications. No, you shouldn't. I also thought Skype wouldn't interrupt me because I set it to I am busy, but okay. Now Fixie gets it. Good, good. Are there other people with questions about this exercise? And to the person who asked yesterday, what kind of questions can we expect about P versus NP? So this is the other sort, right? Here's 2 variations of a problem. One of them turns out to be easy, right? It turns out to be in P. And you can show that using one of the algorithms we've seen before. Tell me which one. All right. Then it's about time to have the break. Does BFS work for an undirected graph? Yes, it does. But remember, for an undirected graph, this problem is trivial, Naomi. Because for an undirected graph, short cycle, well, there will always be a cycle of 2 as soon as we have an edge. Right? If we have just any edge, we can create a cycle of size 2. And so the answer is there one of at most length k? Is going to be yes for any k at least 2. Well, and the graph that has at least one edge. Does that count as a cycle? Yeah, according to our definition, it counts as a cycle. It has 2 different paths, or 2 different edges, with, sorry, two different vertices, and you can go from A to B and then back from B to A. If you want it to be a simple path, so without reusing a vertex, without reusing an edge, then it would be a bit trickier. But then still, yes, BFS would work on an undirected graph. Okay. Just before I send you off into the break, let me tell you a little bit about what I have planned for after the break, and I will be abusing Weblab for this so that I can actually type it for you. Let me zoom in a bit more. So there were some questions yesterday that you submitted. We are going to take a look at BFS versus DFS in terms of implementation. We will be reusing an old lab exercise for that, and I'll show you how we can go from one to the other. This will also answer a question of maybe doing an exercise with BFS or DFS. And walk with us and explain it once more. So I'll be doing that with these. Then someone asked about finding the actual path from Dijkstra. Well, what we'll be doing is finding the actual path from DFS BFS. But you can use the same with Dijkstra. And someone wants me to talk a little bit about how I approach coding. So how do you test/solve implementation problems? So I will try to talk a little bit about that while we're doing the other two things. Someone asked about the spiral traversal, if it is relevant. It is not. So if you have questions about it, I'd be happy to answer them. But for the exam, you don't need to know about how it works. And finally, someone asked, oh, actually, there's two more, sorry. Maybe about hashes. If you have any concrete questions about them, then I will be happy to answer those. Otherwise, the final topic is an overview of time complexity of algorithms. I thought that might be a nice wrap-up exercise. So we can do something like the summary exercises that we did in class. We can try if we can make that work online. So that's what I have planned for the second half of today. If you have anything else to add to this, then feel free to let me know during the break. And I'll see you in about 15 minutes. All right. So, welcome back, everyone. I see no new extra things have popped up. I tried to answer your question, Okumon, during the break. You can let me know later whether this is clear or not. Let's take a look at these things. So let's start with BFS versus DFS and also reconstructing a path from a BFS or DFS. Now I prepared this hang on, just in case, let me hit save. I prepared this in Weblab by copy pasting a homework assignment from 2 weeks ago. So all of you should, of course, have done this already, which means that I think that with only 7 minutes, you should be able to give this an honest go. So yeah, we have a graph, and I would like you to do a depth-first search of that graph and return a list of node IDs that is a depth-first traversal from a certain node n. After you've done this, I will show you how I would implement this and also what I would change to turn the DFS traversal into a BFS traversal. So depth first to breadth first. But first, 7.5 minutes for you to give this a go. As always, if you have any questions, please do post them in chat. See you in a bit. Sorry about that, didn't notice time had passed. So let's take a look. Let me set up feedback fruits to be the bigger thing again. Let me show you my face again. Not that that adds much, but if I want to gesture, then you can at least see. And I'm going to zoom out a tiny bit, just so that a little bit more code fits on the screen at once. Something like this is hopefully still readable, but then a little bit more code fits here. So what do we need to do? We need to do a depth-first traversal. All right, depth-first traversal, depth-first traversal. There were two ways of doing that: recursively, iteratively. When you give me a choice between these two, I almost always prefer iterative, unless we're talking about trees, right? For trees, recursion was really nice. But when given an equal choice, and we have an equal choice here, I would prefer an iterative approach. What do we need for an iterative DFS? We need a stack. Well, Python is not a very nice language in that regard because it doesn't have a stack. Fortunately, it does have a DQ that we can use for this. So my DQ is going to be the nodes I still want to explore. And for starters, I want to explore node N, my starting node. Then I need to keep track of the nodes that I've already seen. And of course, I need to build a result. Now I'm going to do some magic here. And then I'm going to return the result. What is that magic going to be? Well, while there is something to explore, I'm going to get something out of my stack. So let's call it current node. And it's a stack, so I just pop it off. While there is something to explore, I take it off the stack. And now what do I do? Well, now I need to go and look at all of its neighbors. All of its neighbors. Graph library. How do I get all the neighbors? Graph, get node, edges, all nodes. Get neighbors. Okay. I just give it a node and it gives me a sorted list of neighbors. Okay. G.get neighbors of my current node. And now for every neighbor, what do I need to do? Well, I need to go there and explore it. Or rather, yeah, that's what DFS wants to do, right? It immediately wants to go there. In other words, I need to add them to my stack. So to explore, push N. Okay. This is my first idea. This is gonna break for a variety of reasons, but that's intentional. I'm gonna show you how I'm gonna solve that. So let's see what this does. In the meantime, I will answer Shumpum's question, who asks, would you also get full points for a recursive solution? Yes, of course, yes. There is no statement here that says it needs to be recursive or iterative or anything like that. So recursive would also be fine, Shumpum. It's just that I prefer iterative. It has no attribute push. No, correct. It is append. All right. What next? Like I said, I intend for this to break. Yes, this is roughly what I expected. But we need to sit here for a minute before Weblab will finally tell us. This code runs forever. Why is that? What's causing it to break here? Any ideas? I can show you the test if that helps. Why would our code run forever here? Yeah, I keep adding the same things. I don't keep track of the scene. Shumpum and mentioned, yeah, you're both right. If we start in, what do we start? When we start in 0, then I add 1, 3, and 2. But when I examine 1, I add 0 again. And then when I examine 0, I add 1 again. So these two will keep on adding each other forever. So indeed, I need to somewhere check whether stuff is in scene. So if n if n in scene, or rather if n not in scene, then I should still explore it. But that means that I need to at some point add something to scene, right? As you can see when I highlight it, I'm only using scene in one other place now. I also need to make sure I actually put things in there. So let's do that here. There we go. Now this will probably work for this test. Nope, not yet. Because I can't type. Yes, and there's one more thing going wrong. Yes. Okay, so I've added it to scene. The code terminates, but now it returns an empty list. Well, why is that? Because res is my list of results, and well, I never add anything to it. I make it a new list, and then I return this, so nothing gets added. So when I add it to scene, I should also append it to res. Oh, I didn't mean to hit spec test, I meant to hit your test. Now we will see it still fails. Okay, because I want a list of integers, not a list of nodes. So I want to add the ID to res. Okay, what else? Yes, there we go. This is what the test expected to us to return. But now we get this. What is going wrong here? Well, what is going wrong is something from the assignment text. If a certain node has multiple neighbors, these nodes should be returned in ascending order of their values. And exactly that is what happens here, 1 and 2, but we start with 3 instead of with 1. But get neighbors already returns them in an ascending order. So you would think, okay, that if I get them here then, and then I add them, then it should be all right. But remember, this is a stack. So when I get them in ascending order, I get them 1, 2, 3, and I add them to my stack in that order, then 1, 2, 3, 3 is at sorry for that, 3 is at the top of my stack, so 3 is the first one I'm going to consider, whereas it should be the last one I consider. So I need to reverse this list, so that when I put them on my stack, they get reversed back, if you will. So this should now finally fix, yes, our first visible test. We'll worry about the spec tests in a moment. First, let's see if you have questions about this. Naomi already asked us one. Why do you need scene and res separately? It's a good question, right? I could just use n.id not in res. But remember, res is a list, so that would make this check on time. Whereas with scene, which is a set, this check is expected constant time. So it's a small optimization, right? It makes our code a little bit faster, if that makes sense. It costs us a little bit more space, but at the benefit of being faster. Good. I see no other questions at the moment, so I'm just gonna continue for now, run the spec tests. And yeah, one of them still fails. Why is that? Well, imagine, asks, I'll answer your question in a second. So one test still fails. Why is that? Well, you wouldn't normally see this output, so I could show it to you, but that would be cheating. What's going wrong here? Well, imagine we have a test that's a little bit more complicated than this thing. For example, what if it were to look like this? if it has a cycle. Let's see if we can make that test. And let's see if that is what is going wrong. So we have example 2. I'm going to add this, meaning I need to add an edge between 3 and 4. What does our code return? Right, so I have no idea whether this should still be the right answer. But for now, I'm just interested in what does my code return. And this is what I was afraid of. It returns the element 3 twice. Why is that? Well, it finds 2 different paths to get to 3. It can get there immediately from 0, and with its DFS traversal through 2, it will also find the path to 3. And you might think, but we added 3 to scene, right? So this shouldn't happen. Well, we only add something to scene when we get it out of our stack. And at that point, it's very well possible that the node is already in the stack multiple times. So what we should do before doing anything else is check if the current node is in scene, then we should skip it. And we should continue to the next iteration of our while loop. It's similar to what we did with Dijkstra, remember? With Dijkstra it was also possible for the node to be in the priority queue multiple times, but if we'd already handled it once, we should not handle it again. We saw it with Prim, I think, instead of Dijkstra. Let's see if our new test now succeeds. It does, and that should also fix the issue with the spec test, and it does. So there we go. This is, if I just remove this white line, it all fits in one screen. This is our implementation of a depth-first traversal of the graph. Now, Om is asking, okay, scene is perhaps a bit more efficient because it's a set, but could we then not just return this? Well, let's find out. The answer is no, by the way. Yes, and why is that? Well, okay, first of all, because I need IDs, but I can fix that for you. Yeah, let's go for the ugly fix. n.id for n scene. Why does this break? Because scene is a set. It has no ordering. Whereas we want an ordered list here with the nodes in a depth-first traversal order. So unfortunately, this scene is really not going to be good enough to find our answer. It is very efficient to look things up because it is a set, but that is also because it has no order. Does that make sense, Om? Good. All right. Are there more questions about this DFS traversal? Could you also use n for n in current node.neighbors? Let me see. Is that a thing that exists? Yes, but then indeed, as you say, Naomi, you do need to sort them yourself. Yeah. Because indeed we need the sorted version, which is what get neighbors already gives us. But yeah, if you want, you could also use node.neighbors. It's exactly what this thing does for you, right? Node.neighbors, a sorted version of that. So yeah, would be fine. But get neighbors does that for you exactly. Cool. Okay. If there's nothing else, but if more questions pop up, then by all means go for it. I will now show you how we can transform this DFS into a BFS. And for that, I only need to change one single line in this code. Because remember, DFS and BFS were exactly the same thing, only instead of using a stack for BFS, I would use a queue. Well, and Python is kind of nice in this case, because our DQ, our double-ended queue, is both a stack and a queue. So all I need to do is pop from the other side. And now I have created a BFS traversal of this graph. Because rather than using it as a stack, with new things going on the top and me also removing stuff from the top, I'm now still adding stuff to the top, but taking stuff from the bottom, using this thing as a queue. So this should be all. Now it should be BFS, or test should fail, because BFS and DFS traversals are different. Exactly. We could check though, whether this is a BFS traversal, 03214. Test 03214. Yeah, it first gives us all the elements at the distance 1, and then all the elements at the distance 2. There's only one of those. For our other example, it gives us exactly the same thing because it just ignores the cycle. So first all the elements at distance 0, that's for 0. Then at distance 1, 3, 2, and 1. And then at distance 2, that's 4. Notice that in order to have them increasing again, now I should not reverse the neighbors, right? So if that is a requirement, then now I should not reverse. Why not? Because I'm using it as a queue now. When it was a stack, the order would get reversed, but with a queue, the order is maintained, and therefore we would not be reversing the neighbors. So hopefully this cleared up the difference between BFS and DFS in terms of implementation. There's really only one difference, using it as a stack versus using it as a queue. And this is also the reason why I prefer the iterative implementation of DFS. Because in the iterative implementation, the one without recursion, it is trivial to make DFS use, to turn DFS into BFS. Whereas with recursion, a recursive BFS is definitely possible, but nothing to be desired. It's quite horrible to do that. So hopefully that, that difference is now clear. Are there more questions about DFS versus BFS? As I mark the question green in my spreadsheet of questions. If not, I'll give you a couple more seconds here. Then I will do one last thing, which is to show you how we can reconstruct a path. Does a TO always return all nodes of a graph, while a DFS does not necessarily do so? Good question, Naomi. So with TO, I assume you mean topological ordering. So yes, a topological ordering is always all the nodes of a graph, while DFS is only those that are reachable. So for example, imagine there would be a node 6 here, which is not connected to anything else. Then a BFS or DFS from any of these nodes, any of these or any of these, would not return the node 6, but the topological ordering of this graph would. That being said, keep in mind that only directed acyclic graphs have a topological ordering. Remember, only these DAGs, directed acyclic graphs, have one. Now this graph is not directed, so this one does not have a topological ordering. If that makes sense. Good. Okay. Then let me show you how to reconstruct a path. For that, what do we need to do? Well, we need to keep track of how we got to a node. And that really is all. How did we get to the node? So how do we do that? Well, we will keep track using some dictionary. I'll call it previous. And for starters, the previous of n, our starting node, is going to be none, right? That will not have a previous. For all other nodes, well, when I add them to my exploration queue, at that moment I know how I got there. I got there. Oh, I'm calling this thing n. How ugly, because n is also my input variable. Okay, let me quickly fix that. So ng for neighbor, right? So that it doesn't have the same name as this thing. Sorry for that, I should have spotted that before. Python doesn't care because, well, it's Python. But I care because it's a bit ugly. So when I add it to my exploration queue, when I say, okay, I found a new node to explore, that's also the moment where I can register how I got there. How did I get there? Well, I got there from current node, whatever node that is at the moment. And now, in the end, if I, for instance, want, so we're going to make this work only for this test, if I want to find my path to node 4, what do I do? Well, while the previous of my node is not none, I should get node 4. Can I get it? Yes. I get node 4. While the previous is not none, what do I have? Well, I add cur, and I say cur is now the previous of the current. And in order to make sure this is readable for us, I will instead put the IDs in a list. So here we have our output, 4,2. Oh, but hang on. So from 0, I want to get to 4, but I can't go from 0 to 4 directly. Ah, of course, this is now reversed. Why is that? Well, because I start at the end. I start at node number 4 and I look, how did I get there? Okay, and how did I get to the previous one? Okay, and how did I get to that previous one? And okay, how did I get to that previous one? And so on and so forth. So in order for, again, for this to make sense to us, we should reverse it. And then Python is it this? Otherwise I should Google this. Okay. We'll do it like this because Python doesn't like printing things. Yes. Okay, so I reversed it, but that gives me a weird generator object. Need to turn that into a list so Python can print it. Don't worry about this bit, it's just Python syntax. Now we have our path that starts at 0, and then it first goes to 2, and then it goes to 4. Now, of course, this was only a simple graph. I could extend this a little bit. From 4 to 5. From 5 to 6, 6 to 7. 5 to 6, 6 to 7. I also need to create a couple more nodes. And now, if we want to find our path to 7, we can indeed see that we got there via 2, 4, 5, 6, and then finally 7. Does this make sense? So for every node, we keep track, how did I get there? And then we start with the node we want to get to, and we ask, okay, how did we get here? And well, our previous dictionary says, well, you got there via this node. You say, okay, thanks. So the last step in my path must be getting from here to my destination. Great, got that. Now, how did I get here? And our previous says, well, you got there from here. Okay, great. So the penultimate step, the one but last step, must have been going from there to here. Excellent. Can't forget about this. Now, how did I get here? And you continue this all the way until you get to your start. And that way you have reconstructed your path. Does that make sense? Or are there questions about that? And like I said, we can use this with DFS, with BFS, we can use this with Dijkstra. The important thing is so that as soon as we know how we got to a new node, we keep track of how we got there. I see no questions popping up. I'm going to give you another 20 seconds to let me know if you have a question. You can also start by just saying yes to indicate you have a question, and then take a little bit more time to type the question in a moment. And at least I know I need to wait. Do we need to import previous? Ah, I see. No, so previous is a dictionary I made. Right, so it's just a variable that I created. Does that clear it up, Margot? Yes, all right, good, good. Okay. Then I see no other questions. So let's get to our last exercise for today. So I also answered this, I think. I feel that a somewhat complete overview of the time complexity of the most important algorithms would be beneficial. I agree. So let's try and do our summary exercise using Twitch. Now that's going to be a challenge, but a challenge we can rise to and try and make work. So what are we going to do? I'm going to give you only 1.5 minutes. It's not very long, but it should be long enough to create a table that contains as only 2 columns, name of algorithm, well, okay, let's say 3 columns. Name of algorithm, problem it solves, time complexity. Try and list all the different things you have seen in this course. Everything you remember. Perhaps, if you can, do so in reverse order. So start with everything that we saw this week, and then last week, and then the week before. Why is that? Well, because the enter material is most important for you to remember for next week, right? So try and write down all the algorithms you remember, what problem they solve, and in what time they do it. And after the 1.5 minutes have passed, I will collect all of your input and we will create an overview together. But this overview will only contain the things you give me, right? Unless I feel that something very important is forgotten. So try and come up with everything you can so that we have a nice and complete overview at the end. I'll give you 1.5 minutes and then we'll take a look together. All right. So let's hear it. What algorithms did we see and what are their time complexities? And what problems, of course, did they solve? Do they solve? Who's willing to get us started? Okay. First, this thing is deciding to show us more poker ads as usual. I also saw that someone tried to give me an answer. I think it was Naomi, that the bot refused it. That's a pity. I don't know why exactly it refused it. Sorry for that. Stop spamming symbols. Okay. Apparently there were too many symbols in your message. I don't know exactly what that means. Could you maybe... Yeah, there we go. Okay. I see why it may have complained about the symbols. Yes, Dijkstra and A star for the shortest path. So I'll make that 2 entries. Both for shortest path. And both with the same time complexity, namely, indeed, v plus e log v when we use a priority queue. That's one closing bracket too many. This is broken. Is there a this? There is. Good. Yes, thanks for that, Naomi. It's a good start. Dijkstra and A star both solve the shortest path in v plus e log v time. What else did we see? Who's ready to give us another one? Cross call for an MST. Yes, thank you, Vamos. So cross call finds us a minimum spanning tree or MST in O, or theta is perhaps, oh, that's a very nice theta, well, whatever, E log V. Was it E log V? I think it was E log E, but E log E is the same as E log V. Yeah, okay, yeah. All right, we have to sort all the edges. That's E log E. Then we need to go over all the edges and for each of them do that, which is log V time. Yeah, okay, E log V sounds about right to me. Oh, you can't see the tablet, right, because I hit it for the poker ad but never made it visible again. Thanks, Vamos. Here you go. Dijkstra for MSTs. Now, remember, Dijkstra did come up with an MST algorithm, but he already had the shortest route one, so we named it after Prim and Jarnik. But indeed, they also have a minimum spanning tree algorithm that is also in E log V time. Or was it slower? Yeah, maybe. Yeah, because it was essentially just Dijkstra. Yes. So E plus V log V. And then I am going to change this to E log E, even though that is the same, because E is upper bound by V squared. That dropped off the page. E is O V squared, but E log E is a little bit more precise in that sense. What else? Well, I'm going to add some here and you can tell me what they do. So we saw BFS and DFS. They do something and they have a certain time complexity. We saw a way to get topological orderings. Well, what do? They give you a topological ordering. And that had a certain time complexity. But we saw a little bit more. While I'm waiting for you to tell me what BFS and DFS do and what time complexity they have. Okay, so this exercise clearly works better in a classroom, the more you know. Let's see if you can finish this off regardless. Union find, yeah, I like it. It's technically speaking not an algorithm, but a disjoint set data structure. But let's add it regardless. Oh, it's complicated. Efficient was basically it. BFS and DFS determines which vertices you can reach, exactly. Find reachable vertices. It was a little bit worse than Vita V though. It was Vita V plus E, as Famos is pointing out. So almost there, Naomi. Remember that if we had more edges, then it would still take a little bit more time, this BFS and DFS traversal. Because we did something for every edge and we did something for every vertex. So V plus E, whichever one was the biggest was the one that would win out. Do we remember the time complexity of topological ordering? I mean, how does it work? Well, first we go over all the vertices. We need to remove all the edges from the graph. And is there anything else we need to do? Well, not really. So I think it was also just V plus E, unless I'm now forgetting a step. Go over all the vertices, find the ones with no incoming edges, repeatedly remove all its edges, so we do something for every edge, check whether the vertex now still has zero, then add it. No, I think it's just V plus E. So notice that for me personally, I can imagine this might be different from you, but what I remember is this. And what I can derive is this, right? I remember what does the algorithm do and how does it do it, and therefore I can derive the time complexity. So that's something I don't bother remembering. But like I said, I can imagine this might be different for you. Oh, this is not at all what I wanted. Now, of course, before the midterm, we already saw lots of other things too. There's only one thing I want to reiterate. One algorithm, namely sorting. Sort a list. We can do in theta n log n time. For example, with merge sort. It sorts a list in n log n time. I think these are the most important ones to remember for the end term. Of course, we saw much more, right? We talked about binary search, we talked about finding the closest pair of points, all this kind of stuff. But I think these are the most important ones for now. Okay. We are a little bit over time already, so there's only one last thing I want to tell you about, which is first day's tutorial. As I mentioned yesterday during the lecture, first day's tutorial will be there in the sense that I will be there to answer any questions that you may have. I think we will not be using Twitch, but we will probably be using Brightspace for this. So Brightspace also has something like this. And since I really want it to be Q&A only, so you can drop in, ask me questions and leave again if you have no questions. I think Twitch isn't the ideal platform for this because I'd have to be live for 2 hours, just sit here, do nothing unless you have questions. Brightspace allows me to do that a little bit easier. But I'll let you know tomorrow afternoon what platform we use and how. If you have any questions at all that you would like me to answer during the tutorial, please let me know via Brightspace. And then I'll see whether I can answer them there or whether it makes more sense for me to take my tablet out and draw you something. I think that's all I wanted to talk about today. So thank you again for being here. Good luck in your preparations. And if you have any questions, I'll be happy to answer them on Brightspace or on Thursday during our Q&A session. See you then.